It is my pleasure now to introduce our keynote speaker, Mr. Robert Pearce. Mr. Robert Pearce is the Associate Administrator for NASA's Aeronautics Research Mission Directorate, ARMD. He manages the agency's aeronautics research portfolio and guides its strategic direction, including research in advanced air vehicle concepts, airspace operations and safety, integrated aviation systems, and the nurturing and development of transformative concepts for aviation. He has experience in all aspects of aviation research and development, including serving as the Deputy Director of the FAA-led Next Generation Air Transportation Systems Joint Planning and Development Office. He began his career as a design engineer at the Grumman Corporation, working on such projects as the Navy F-14 Tomcat fighter and DARPA's X-29 forward swept-wing demonstrator. He earned a Bachelor of Science degree in Mechanical and Aerospace Engineering from Syracuse University and his Master's of Science degree in Technology and Policy from the Massachusetts Institute of Technology. Please join me in giving a warm welcome to Mr. Robert Pearce.
Thank you so much for the Thank you so much for the introduction. And thank you so much for the warm hospitality I've found here since I've been here. Started yesterday, but had the opportunity to go around and see some of the facilities and some of the people here at Ohio State. I gotta tell you, it's just wonderful. The quality of the people is amazing, but also the passion that you bring to your work. That's incredible, and that's really what makes the magic, right? It's that the quality and the passion together that allows us to push to the future. And I haven't been any place that exceeds what you bring here at the Ohio State University. So thank you for all of that. So today I'll give you. You've heard a lot this morning about the details of advanced air mobility and we're doing in NASA as well as what everybody else is doing across the state of Ohio and other places. And I want to step back a little bit and give you a little bit of a vision for where we look to the future in aeronautics and advanced air mobility. But first, I did want to just give a shout out to all the folks I've met here in the folks across the entire state of Ohio that are working so hard to bring advanced air mobility to life. It really is, and this is absolutely true within NASA, it is the partnerships that make this happen. Without partnerships, none of it is possible. There's no one organization, even as great as the Ohio State University is or NASA is, there's no one organization that can make these big things happen. It is only through the combined effort of great organizations across the United States, and certainly in the state of Ohio, that enable us to do these things. None of this is risk, none of this is easy, and none of this is going to be done quickly, right? It's going to take time to work on. So I just really appreciate everything that you guys are doing now and the tenacity to stick with it and to see it through to fruition. So let me dive into a few words about where we're heading as an NASA Aeronautics Research Enterprise and what we're doing with respect to happening. So I like to talk about 4 elements of vision for the future, and you can see them here on the screen. In the upper left-hand corner, the notion of sustainability, right? As an industry, aviation as an industry has to become absolutely sustainable as we move forward. There are an aviation climate action plan that has been published, and the goal is to get to net zero emissions by mid-century, by 2050 net zero emissions. If you've been paying attention to this, that's a big leap from where it was just a couple of years ago, where it was a 50% reduction in CO2 emissions by mid-century. Now we've left to, because that wasn't hard enough, we left to let's make it climate neutral by mid-century. That's obviously a difficult job to do. That's going to require technology. It's going to require a lot of innovation. So within NASA, one of the things we're doing is we've just started what we call a next generation. That's what we call it the Sustainable Flight National Partnership. Sorry, the Sustainable Flight National Partnership. We just started this a year or so ago. But it's the result of decades of work on some fundamental technologies that have the opportunity to transform the future of aviation. Things like hydroelectric propulsion being worked right here at Ohio State. I was just over yesterday with at the Center for Automotive Research, CAR. And when they told me I was going to go there, I said, why are you taking me to the Center for Automotive Research? And it's because they're right in the middle of doing work on megawatt class electric propulsion. And it's just fantastic, right? Just the way they think about this, that while their background is in automotive research and obviously the electrification of the automobile, but when they took a look at this problem, they saw that, the parameters are different, but many of the challenges are the same. And so they were able to be a part of a large team, Ohio State and others in industry, to go ahead and say, we're going to build and test a high energy density, high power density, megawatt class electric motor and the power electronics that go with it, and I'll put it into the NASA electric aircraft test facility, just in another part of your state, right up outside Cleveland. So that's going to happen here in the not too distant future, just in a few months. We're looking forward to seeing that installed in the new facility. But that's just a testament to the multidisciplinary nature of the kind of things we need to do. So that's one example of a technology that is moving rapidly, and that's going to find its way into the next generation of transport aircraft. That's the goal. Now, a lot of work to be done to make that happen, but that's the goal for the next generation. So just think about in the 2030s when things like 737s, A320s get replaced, what's that next generation of aircraft? And we want that to be 25, 35% more efficient than best in class today. Those numbers don't happen without some big innovation. So hyper-electric propulsion is one of those. Another one is, it's just better improvement on the turbine itself. Let's reduce the core size of the turbine, increase the thermal efficiency, and then marry that up into a hybrid. So let's look at that right from the start as being able to be hybridized. So the ability to take off a lot of power, put a lot of power to the shaft. So not easy thing to do. So that's another big part of this. So a couple of big propulsion projects for that next generation. On the vehicle side, we're looking at aerodynamics. So what's the next set of configurations that would improve the aerodynamics? And so you can kind of see that picture there, that iconic picture of what we call a transonic thrust brace wing, very high aspect ratio. So I think as everybody in this room knows, increase the aspect ratio, reduce the induced drag, and get a more efficient aircraft. Now, difficult to do because now you're going to have a much thinner wing to make that happen. So the structures become hard. But and we want to make sure we have a lightweight structure, right? So we're not, reducing the benefits you get from the drag reduction by increasing the weight of the airplane. So we've been working on that for a long time. That's not the only configuration. There's with other opportunities to look at advanced aerodynamics, advanced configurations that can fundamentally create a more efficient vehicle. And on top of that, we know that whatever the next aircraft is going to be composite. And if you think about single aisle, they have to be produced at high rates. Today, we can't produce economically. We can't produce composite aircraft at the rates that we want to produce in our next generation single aisle. So high rate composite manufacturing is the fourth area of technology we're looking at relative to that next generation sustainable flight partnership. So, and then the final area is operations. So if we're going to have a very highly efficient aircraft and burning sustainable aviation fuel, because that's another key to getting to net zero emissions. You got to have a fuel that on a net basis, provides low or near net zero emissions. You want to do that as efficiently as possible. So we're looking at the airspace operation component of this to make sure it can fly optimal trajectories and gate to gate. Now, any one airplane is pretty easy to fly an optimal trajectory, but the problem is when you have thousands of airplanes flying at once, when you have weather and you have other constraints, how do you make sure all those aircraft can fly optimal trajectories? So that's the challenge there. And we also, it's not just carbon, it's not just a carbon issue. There are things like contrails and other things that we need to think about. So how do we build our trajectory management, optimization tools, and so forth to account for trying to eliminate the production of contrails in flight. So there's a lot of complexity that goes with that as well. So it's an exciting time to bring some of those technologies we've been working on for decades up to that higher TRL. And again, Ohio State is a part of that in some very exciting ways. But we're also, to really get to that mid-century point, there's a high dependency right now on the ability to scale up sustainable aviation. It's something like 35 billion gallons a year. Basically, it's biofuel. That's not obvious. That is a doable thing. That is the goal. That is the national goal. And DOE and FAA and others are right in the middle of trying to make that happen. So I think that's something we all have to strive for. And it's not necessarily a technology issue. It's a scalability issue. Can you scale up the production of those fuels to that level? Within NASA, we look at it and say, we've got to be providing some options. Who knows if that is going to be the pathway to the future? Obviously, in Europe and other places, hydrogen is on the table as an alternative source of energy for the future. Hydrogen could match up very well with electric propulsion and so forth. So at the same time as we are doing our Sustainable Flight National Partnership, we're also looking at low TRL to say, what are some more advanced concepts, more advanced ideas that we can use to get to that mid-century zero emissions aircraft and system and so forth. So we're starting those today. And that project that I was telling you about earlier relative to the megawatt propulsion that we've got Ohio State leading, that was done through what we call the University Leadership Initiative. We are, in this budget, we have increased the amount of money that's going into the University Leadership Initiative, and we're adding a special topic on zero emission aviation. So I'm looking for Ohio State and others to be putting the next set of, and the next solicitation is going to be like in a few weeks, it's next month. I don't know the exact date, but I'm looking to Ohio State and others to be putting in another proposal that goes even further, that's bolder, that takes those next steps and to get us on that path, right? So the folks in this room, folks in other rooms like this, other universities, really want you to push as far as you can, think big, and get those proposals in, and let's get that path going. Let's get that process and that partnership going. So there's a lot going on. It is the biggest part of our portfolio. Efficiency, sustainability is the biggest part of our portfolio. Will be for quite some time. But we've got a pretty large budget, so we can do more than one thing. So we've got a few other things going on. So right below that, ultra efficient transport, you see high speed commercial flight. So it's another dream ever since the Concorde started flying, and is can we have commercial supersonic flight? Of course, Concorde didn't. It did have a niche, but it never became a real mainstream form of transportation because of the constraints on supersonic flight. And so the Concorde, obviously, the overland boom was way too loud, and so the prohibition against overland supersonic flight, landing and takeoff noise, upper atmospheric emissions, just the inefficiency of supersonic flight. Those are all things that need to be solved. What we did at NASA, because of the interest within the community, to see if we can't solve these problems. So we can't do it all at once, especially not at that high TRL, but let's take on a big challenge. So we took on the solid boom challenge. Said, can we soften that boom so you could fly supersonically over land and not have a large boom, not create a large boom that would be unacceptable to communities. Of course, it's been 50 years since the development of Concorde, so aerodynamic structures, a lot of things have come a long way since then. And now we do have the tools to design, to shape an aircraft that actually has a very low noise signature, overland noise signature. Right now, as some of you may know, we are building the X-59 low boom flight demonstrator. I think this morning, if I'm not mistaken, it was in structural test at Fort Worth because it's almost built. The structure is all done. It was in structural test there. We did some fuel system testing. Ironically, we put it on a back of a flatbed, large flatbed truck, and it was tooling down the road at 55 miles. Supersonic airplanes tooling down the road at 55 miles an hour, all the way back to Palmdale, California. So that took many days. For something I should have sticked on. So to get from what, but I think they just unloaded it this morning. I haven't read my emails lately, but I think they just unloaded it to do the final integration. Get the engine installed, power on testing, get the final system checked out, get the taxi testing, and get the first flight. lot of work to do, but we're hoping to get it done before the end of the calendar year. We'll see if there's no glitches and so forth. We could probably do that. If not, it might take a little bit longer. But the whole idea there is to build an airplane that essentially produces a low boom, and then take it out over communities and see what people think. And that's it. And gather that community response data and hand it to FAA, and ICAO would say, what do you think? We produce a standard, a noise standard for overnight supersonic flight. So we think it's around 75 dB, perceived noise level of 75 dB. It's about and you think of Concorde, I think it was around 105. So, if you know acoustics, that's a gulp, an enormous gulp in noise. It's about if we're standing here today, it'd be kind of like distant thunder, rumble of thunder, or maybe a car door closing outside. It's about that level of noise. So if you're paying attention, you might hear it. In this room today, for those of you that are listening to me wouldn't hear it. For those of you that zoned out, you might. So, but we're going to take that out over communities, and we're going to scientifically survey. So here's an interesting problem, right? So NASA's, you go anywhere, right? Like people have NASA T-shirts on, and so it's wonderful to work for NASA because everybody kind of loves NASA. Right? So here's a scientific problem for you, right? So we tell the community we're going to come do this flight, and you're NASA, and it's like, oh yeah, let's I want to do that. I want to be part of the survey. It's like, we don't really want you to be that enthusiastic. We want you to be objective, right? We don't want you to like the fact that so it is a hard problem, right? To do this work and really get objective response from the community and say, hey, this is really what I think. And we can do things to shift the noise a little bit with this, flight slightly different altitudes, slightly different speeds and so forth. And we can actually change the outer mode line a little bit, so we can actually modify the sound a little bit, and in order to get a dose response relationship there. So it's going to be really exciting. I mean, it is getting real, and there's just a lot of interesting things. We've got microphone arrays, and we're thinking about. And so when you're in this community, you got to be microphone because you need to know what noise you're actually hearing, right? So there's hundreds of these things, and so you got to put them out. Like we don't have enough money to have a person watch every one of these microphones, right? So now we're like, well, maybe we have kids adopt our microphones so that they don't walk away, and chain them to trees and stuff. So it's really interesting. So it's exciting. But we think we can do it. We think there is in fact a noise signature that's acceptable. We'll get that low noise standard along the way. Because of the work we've done, we'll deliver the tools and methodologies that was used to build this airplane to the industry so that they can in fact build an airplane, they can in fact design an airplane to meet these standards. That's really the goal behind all this. So it's just a really interesting project that we're right on the verge of really taking to flight. I'm going to go to the upper right hand box. So I'll save advanced air mobility for last. But you think about, imagine in your mind advanced air mobility. Imagine supersonic flight, right? Going to get a little bit higher altitude, the upper E airspace, right? Think about ultra efficient transports. Think about high altitude, long endurance UAS and so forth. And all of a sudden, you start to see small UAS, right? All of a sudden, you start to see the complexity of the airspace that's ahead of us, and the complexity of the safety problem that's ahead of us. We want to introduce all this technology in order to get the benefits of this technology. But I can tell you with the FAA guys staring at me right now, it ain't happening if it ain't safe. And it's the vehicle that needs to be safe, but it's the total integration of those vehicles into a system that has to be safe. And so we need to think about how we manage airspace and how we manage safety going forward. So everything we are learning relative to AI, machine learning, and so forth, everything we've learned relative to how you put together digital networks and do third-party services and so forth, everything has to be brought together in order to be able to do this job and to allow all of these types of use cases to be part of the system. So you can imagine that same data that we would use to manage the airspace, to make sure that everybody is flying efficient trajectories and maintaining separation and so forth. All that data, it's a rich database to also put learning algorithms in to see, are there, what are the patterns in the system, and are there things that are giving us hints that there may be hazards or risks or threats and so forth in the system building. Let's learn that, mitigate it before they become incidents in the system, so we don't go down the path that we have in aviation in the past, whereas we have an incident, we have an accident, we learn from it, we correct it, it doesn't happen again. We don't want to go down that path with these new systems. We want to learn from the data so that we don't get to the incident accident and we have a safe system from day one. So that's going to take a lot of work. We have a vision for doing that. What I've seen here at Ohio State, you guys have people that can contribute to that. I would recommend that you get with our, Janet Army somewhere, you can talk to some of that. So it's really exciting times, and that all leads down to that lower right-hand box of advanced air mobility. So one of the most exciting things I think on the horizon, right, is advanced air mobility. The ability to move in new and different ways, right, and provide mobility that doesn't exist today. And when we provide mobility that doesn't exist today, it's not just going to be the obvious things that they're used for, right? We all know that the industry wants to do air taxi and things like that, move cargo. But I'm asking you to think bigger than that. Think broadly about how it could affect how businesses, how organizations operate. Think about Ohio State. You are an enormous campus, right? And you probably have satellite campuses, right? And so forth. Imagine if you had a UAM system that actually linked your campuses together. So a professor could be, could teach a class on one campus and teach a class on another campus, all very efficiently in the same day and so forth. You can change your value proposition through the use of new mobility options. So this is, and all my charts, like David Hackenberg, who's sitting here, who's my #1 expert in advanced air mobility. These are, I don't have any charts that he hasn't produced, so you can always read them better than I can. But I'll give you my spin on this stuff. So this is a sample of, this is a, if you're an enterprise architect kind of person, this is called an OV1, an operational view 1. It kind of gives you a perspective of the vision of what advanced air mobility might be like, and it's a compilation of many individual use cases that people have envisioned in terms of how they could use this capability. So as I said, eVTOL, small package delivery, larger package deliveries, cargo delivery, urban to urban operations, urban to suburban and to rural operations, and so forth. Medical, and I'll talk a little bit more about that because it's one of my most favorite things. And I'll talk about wildfire a little bit as well, because I think there's another thing I would have folks think about is think about the public use cases that are out there, because the way to get the public excited and supportive of something like this is to have it do something that will bring greater quality of life to people in Ohio and people across the country. And that's, I think, where the beauty is. And so this chart I really like is you see the kind of the centroids, right? And that public good one, the two that really excite me, one is, and it's happening right here in Ohio. And I think it's just fantastic. You've got world-class medical facilities. You've got essentially the start of, or actually the practice of a community of practice, right? Of the medical community coming together and saying, okay, what would we do with this? And you're starting to get people to think about, look at, not that you guys are doing that. I think you did a test case with organ delivery and so forth, which is absolutely fantastic. But there's talk about, rather than moving patients to hospitals, why don't you move doctors to patients? You just would never think about that, right? Because how would you get a doctor to, doctors it's a valuable asset, right? You don't want to take them out of the commission for too long, right? You want them to be performing their services as efficiently as possible. So you don't have a transportation system allow you to do that. This could be it. If I could get a doctor to where the patients are when they need to be there, to do that in 15 or 20 minutes, all of a sudden you can change the way healthcare is provisioned. All of a sudden the decline in health access in rural areas has some solution, right? So now these world-class medical facilities you have to increase their radius of operation, right? So that's an absolutely fantastic use case that we really need to be working on. We need to make happen. And I think when we do that, you're going to see the population understand the impact of doing this kind of work. Another one is on wildfires, right? So I think, as many of you know, wildfire is an absolute crisis in the United States. There used to be a wildfire season, and now it's 12 months. It's literally 12 months of the year there are wildfires, right? So how do we manage wildfires today? If you're familiar with it, the aviation component is is in the dark ages, right? I mean, they fly only visual flight conditions, daytime operations, and low density, right? Because they have an air boss sitting in an airplane over all the traffic, looking down and separate, making sure that everybody is separated. I mean, that is just an antiquated way to do business. If they were able to fly at higher density, if they were able to mix small UAS, mid-sized UAS, large aircraft together in higher density, if they were fly at night, so what the wildfire managers say, fires lie down at night, right? That's when they want to put retardant on fires, is when the fires are more controlled, right? So, but they got to be able to get there. They'd love to be able to surveil these fires 24/7, right? NASA, in fact, does. We give them great data from satellite imagery and so forth, so it's DoD and others. But it's not dynamic enough, it's not integrated. So they'd love to be able to put a small UAS where the fire is to see where it is, or a somewhat larger UAS to look at the whole thing. Give them much more spectral accuracy, much more geographic accuracy where the fire is, and dynamically where it's going and so forth, so they can put their assets. Imagine having UAM vehicles that can pre-position equipment where it needs to be based on knowing where the fire is going. I mean, you could just imagine what this could do if we had this kind of capability. So it's just a fantastic opportunity to do public good operations and have the public really appreciate what this brings. And I have, and I'm a fan for passenger transport, cargo transport, and so forth. I mean, that is going to revolutionize how we all live and work and so forth. Allow us to be, Davis doesn't miss a day telling me that he wants to fly to work, and so do I. So I think there's those opportunities to do that, and I think all of it together does just what in that little bag box down there, right? $115 billion of potential market opportunity by 2035, and I think that depending on how this plays out, that could maybe be an overestimation, but it could be an underestimation, right? 2035, there's a lot that we can do in that 13 years of time to make this happen, but it's not going to happen without the hard work and research that you're doing here, the partnership with the state of Ohio, trying to being first again in aviation. And just to say a few words about what we do and how we work with others. So we've looked at this in a couple of different ways. Obviously, the challenges, the technical challenges are across things like vehicle development, operations, and the community is. I mean, I don't even know what the number is today, but there's so many eVTOL designs you can't even keep count, right? Clearly, all of those are not going to be successful. There's going to be a handful that are successful, and some of them are in certification today. Folks like Joby and others are in certification today. They got a ways to go, but there's some really well-funded. Those first-generation vehicles are well underway, but there's a lot of work, for future generations that need to be done as well in vehicle development. So noise is a big issue. So they're building as best they can low noise vehicles today, but we're going to need techniques for even better noise characteristics going forward, because as density increases, noise annoyance goes up as well. So we're going to have to look at operational techniques as well as better rotors and other systems in order to reduce noise. Obviously, the reliability of these systems has to go up. So the work we're doing in electric propulsion and other things at high energy and high power densities, we've got to get better at the reliability and so forth, making sure these systems operate reliably every single time, right? So there's a lot to be done in vehicle development and operations. Airspace design and operations is another area that if I include vertiport in there, you can think about, and Davis talks a lot about this, think about the vehicle automation, think about the airspace automation, think about vertiport automation, think about safety automation, right? All of those things, we don't want the vehicle folks going off on, in one stovepipe, airspace folks going in another stovepipe, and the vertiport folks going in another stovepipe. We want to look at that automation as a whole, right? Because we want to make sure that it is, in fact, an integrated automation system where we know what the functional allocations are across those things, and we know there's integration, so that it all works smoothly and all works safely, and all that data is available to do this efficiently. So there's a big job to be done there in automation. Community integration, again, the state of Ohio, the partnerships here, that's what it's all about, trying to get some early operations, getting that early community integration, learning and doing and evolving from there. So we're doing that through those categories in 3 different ways. Our research and development that we do inside NASA and that we support externally as well. So I saw some things where you guys are helping us on some key research areas for, as a part of that fundamental research that we need to bring to the table to advance the technology that will allow us to do this. At the same time, we need those ecosystem partnerships, right? And so we're operating a large set of ecosystem working groups that operate that meet almost continuously, hundreds to thousands of people. Because in order to make this happen, we all have to be talking, right? That everybody is bringing something to the table, whether it's an infrastructure provider, a vehicle provider, an airspace provider, a research provider, all have to be talking, all have to be collaborating if this is going to work. Because none of this can be done in a stovepipe. So those working groups are awesome. I hope a lot of you are part of that. And then finally, and the thing that I think brings it all together is that national campaign series that we're doing, where it allows us to bring technology, especially things around automation and so forth, let the industry bring things together. And if we've done it right, if we've done it from an architecture perspective, we've done it from an integration perspective, we can actually demonstrate, start small, start simple, then build out. We demonstrate that it all works together, and it all works the way we think it's going to work. But guarantee, right? We do it because we're going to learn, right? We're going to learn in terms of, hey, that didn't quite work the way we wanted to, but we're also going to learn in terms of what's that next step we need to take to even go further. And so we break that down into a series of campaigns over every couple of years that allows us to bring the community together. And again, I know Ohio and Ohio State's going to be a part of that. You have your corridor that you've outfitted with great infrastructure. So I know you guys are going to be a part of that. So my hat's off to you for doing that. So actually, I have no idea why I thought. So that's what I got. Please, again, nothing we do in Mass Aeronautics, we do alone. We do it with the community because that's the way to make progress. And so I definitely ask all of you to think about how you, if you're not in conversations with us today, if you're not looking at how we can work together today to think about that and participate in the programs that we have. It's important. So with that, I will stop, and if there's a few minutes, happy to take a couple of questions. If not, I will bid you the good rest of the total questions.
Thank you, Dr. Pearce, for joining us. One thing I wanted to know, you touched on this a bit, but you mentioned how the industry is new. It's not just improvements anymore that we're making to aviation. We're contributing to revolutions right now. The work that all of us are partaking in here is truly a new age in the sky. And the symposium is one of the many pieces in Ohio that go to showcase that we are ready to step into that leadership position. We are ready to contribute to these national campaigns in massive and meaningful